Waves are literally everywhere. They're in the light you're using to see this, the sound that's hitting your ears, even the water in a lake. But have you ever stopped to wonder what happens when these waves actually meet? Well, it turns out there's a surprisingly simple set of rules that explains almost everything, and it unlocks some of the most amazing things we see and hear every day. So, let's dive into the simple logic behind this unseen world. Just look at a lake's surface. At first glance, it looks totally chaotic, right? Just a random jumble of ripples and waves crisscrossing all over the place. But what if all of that complexity, all that apparent randomness, actually comes from one incredibly simple idea?
And that big idea? It all comes down to what happens in that single moment when two or more waves are in the exact same spot at the exact same time. This is where the real magic is.
Now, physics has a fancy name for it, the principle of superposition. It sounds a little intimidating, I know, but it's just a formal way of saying something really straightforward. When waves meet, they don't crash into each other or bounce off. They just pass right through one another, and for a split second, they merge. That's really it. The simple idea is waves just add up. You can think of the peak of a wave, its crest, as a positive number, and the bottom of it, the trough, as a negative number. At any point where they overlap, you just do the math. And that one simple rule, it unlocks everything else we're about to explore. And what's so wild is that this simple act of addition leads to two completely opposite but equally powerful outcomes. Waves can either build each other up into something bigger, or they can completely wipe each other out. First, let's talk about what's called constructive interference. This is what happens when two waves are perfectly in sync. Their crests line up with crests and their troughs line up with troughs. When they meet, they combine their energy. Their amplitudes add together, and for a moment, they create one single, much bigger wave. Then they just pass through each other and continue on their way, totally unchanged. Okay, but what if they're perfectly out of sync? This is where it gets really cool. This is destructive interference. The crest of one wave lines up exactly with the trough of the other. So a positive meets a negative, and for that brief instant, they can completely cancel each other out. You're left with nothing, just stillness. And this isn't just a thought experiment. It's the science behind one of the coolest gadgets you can own, noise-canceling headphones. See, a tiny microphone on the outside listens to the ambient sound wave. The headphones then instantly create a perfect copy of that sound wave. And here's the trick, it's perfectly out of sync. The two sound waves meet right at your eardrum, destructively interfere, and poof, the result is silence, literally created from sound. Amazing, right? Now, this whole interference thing gets even more interesting when a wave starts interfering with itself. Yeah, this happens when waves get kind of trapped and have nowhere else to go. Let's ask a simple question. What happens when a wave hits a wall or some kind of boundary? Well, it reflects, right? It bounces back. And now that reflected wave is heading right back into all the new waves that are still coming in. And if you get the frequency just right, the self-interference creates this incredible pattern that looks like it's frozen in time. We call it a standing wave. Now, the wave is still moving, of course, but the pattern of constructive and destructive interference is so perfect and stable that it just looks like it's standing still. And if you look closely at this pattern, you'll see two key parts. The points where there's perfect destructive interference, those are called nodes. They don't move at all. And the points where there's maximum constructive interference are the antinodes. That's where the wave is swinging back and forth with the most energy. How that wave reflects actually depends on what it hits. If it hits a fixed end, think of a harp string tied down tight, the reflected wave actually flips upside down. But if it hits a free end, like the tip of a flag flopping in the wind, it reflects right side up. And these two different types of reflection create all sorts of different standing wave patterns. Okay, so we've seen how interference can create these cool visual patterns, and how it can even create silence. But you can also hear interference in a really distinct way. When you have two sounds that are almost the same frequency, but not quite, something interesting happens. They constantly drift in and out of sync with each other. This creates a pattern of constructive and destructive interference that our ears pick up as this rhythmic wobble in the volume, that classic wah 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 sound. We call that an acoustical beat. And this isn't just some weird physics quirk, it's a super important tool for musicians. If you're tuning a guitar, for example, you play a reference note and the string you're tuning at the same time. If you hear that wobble, that beat, you know you're out of tune. You just adjust the string until the beat goes away. And that's how you know the frequencies are perfectly matched.
So, everything we've looked at so far is about waves interfering with each other in space. But what happens when the thing that's making the wave is actually moving through space?
Oh, you absolutely know the sound. It's that high-pitched whine of an approaching ambulance that suddenly drops to a lower groan as it speeds past you. That neom. It's probably the most famous, most common example of wave physics in our daily lives. But why does it do that? Why does the pitch of the siren seem to change so dramatically? Well, the answer is something called the Doppler effect, and it has everything to do with how motion messes with waves. So as the siren is moving, it's basically chasing its own sound waves in the direction it's heading. This squishes the waves together, compressing them. And behind it, the siren is moving away from the waves it just made, which has the effect of stretching them out. So what does this mean for you just standing on the sidewalk? It means the frequency of the wave you hear actually changes. Those bunched up waves arrive at your ear more often, which means a higher frequency, and our brain interprets higher frequency as a higher pitch. Once it passes, the spread out waves arrive less often, lower frequency, and you hear a lower pitch. And this is not a subtle change. Let's put some numbers to it. If a siren is blasting out a steady 800 hertz tone as it's coming towards you, you will actually hear it as 863 hertz. The instant it passes, that sound drops to 746 hertz. The siren itself never changed its sound, not once. Only your perception of it changed, all because of motion. So when you think about it, it all comes back to that one elegantly simple idea. Waves just add up. Through constructive and destructive interference, that one rule explains how you get silence from sound, how a guitar string makes a note, how musicians tune their instruments, and even the sound of a passing siren. It really makes you wonder, doesn't it? What other things in our world that seem so complex and chaotic are really just simple physics in disguise?